There is a particular kind of stillness that arrives late at night, when the air grows cold and the wind moves through distant trees, with a sound so faint it might be silence itself learning to breathe. The ground beneath you feels solid, reliable, the way it has always felt. And yet somewhere in that quiet darkness, a question begins to form. Not urgent, not demanding, but patient, like something that has been waiting beneath the surface for a very long time. This is a place for wondering about what exists below, not in the shallow sense of buried objects or hidden caves, but in the deeper sense of scale, of layers that extend so far down that the mind struggles to follow, layers that have been there since before anything human walked above them, quietly holding the world together in ways we almost never consider. If this kind of quiet reflection feels right to you, you can subscribe to Quiet Science and continue these slow journeys with us, moving through the hidden parts of the world at a pace that allows thought to settle and expand. Tonight, we begin at the surface, where familiarity ends and true depth begins. The ground you stand on seems stable, feels permanent, but it is only the thinnest boundary between the everyday world and something vast, a structure so immense, so layered, so removed from human perception that most of us live entire lives without ever pausing to imagine what it actually means. We think of the earth as solid, as finished, as a backdrop for our movement, but that is only because we exist at the very top of it, in the shallowest fraction of its total depth. Beneath that surface lies an architecture of pressure and heat and slow transformation, extending thousands of kilometers down through layers that have been forming, shifting, circulating for billions of years. Layers that shape continents and generate magnetic fields and absorb the energy of distant cosmic events. All of it happening in a darkness so complete that no light has ever reached it, and at scales so enormous that the human body, standing on the surface, exists in a dimension almost unrelated to what unfolds below. When you place your hand flat against the ground, what you touch is not really the earth, not yet. What you feel is the surface residue of the earth, the weathered dust of ancient mountains, the decomposed remains of forests that stood centuries ago, the sediment carried by rivers that no longer exist, all of it compressed into a thin biological film that clings to the planet's outer shell like moss on stone. Soil, in the places where it exists at all, rarely extends more than a few meters down, and even then it is fragile, temporary, constantly being created and destroyed by wind and water and the roots of growing things. It is the zone where life and rock meet, where organic matter mingles with mineral fragments, where earthworms tunnel through darkness and microbes break down what was once alive, transforming it into something the next generation of roots can use. We live on this layer, build on it, depend on it entirely, and yet it represents almost nothing in terms of the planet's actual depth, a coating so thin that if the Earth were reduced to the size of an apple, the soil would be thinner than the skin, barely visible, easily rubbed away. Beneath the soil, if you could descend just a little further, you would encounter bedrock, the first true stone, the place where the weathered surface gives way to something older and more permanent. This is still shallow bedrock, fractured and broken by frost and roots, infiltrated by groundwater seeping down through cracks. But it is recognizably different from the loose material above. Here the rock has names: granite in some places, limestone in others, sandstone, basalt, schist. Each one a record of processes that took millions of years to complete, processes involving heat, pressure, the slow accumulation of sediment on ancient sea floors, the cooling of molten material deep underground, the collision of tectonic plates that folded and compressed what was once horizontal into vertical walls of stone. If you were to drill down through this upper bedrock, even just 100 meters, you would pass through layers that formed at different times, under different conditions, each one preserving a fragment of the planet's history in its mineral composition, in the way its crystals are arranged, in the fossils it contains or does not contain. But even this zone of soil and shallow fractured bedrock, this place where water still moves and temperatures still fluctuate with the seasons, is only the entrance. It is the part of the Earth that weather can touch, that human activity can disturb, that feels connected, however tenuously, to the surface world of light and air and living organisms. Go deeper, past the reach of tree roots, past the depth where groundwater circulates freely, past the zone where freeze-thaw cycles fracture stone, and you enter a different realm entirely. Here, the rock becomes continuous, unbroken, no longer subject to the daily or seasonal rhythms of the surface. The temperature stops fluctuating and begins to rise steadily with depth, increasing by roughly 25 to 30 degrees Celsius for every kilometer you descend. A gradient that exists because the planet's interior is hot, vastly hotter than the surface. And that heat is always trying to escape, always radiating upward through solid stone, at a pace so slow it takes millions of years for warmth generated deep below to reach the open air. This is still the crust, the outermost solid shell of the planet, but already we are moving into a regime that exists beyond human experience. No natural cave extends this deep. No mine, no matter how ambitious, reaches more than a few kilometers down. The deepest boreholes ever drilled, scientific projects that took years to complete, using equipment designed specifically to withstand the heat and pressure, have penetrated roughly 12 kilometers into the crust, and even that represents less than 1% of the distance to the Earth's center. What those drilling projects discovered was not emptiness or hollow chambers, but continuous rock, growing hotter and denser with every meter, rock that had been sitting there, undisturbed, for hundreds of millions of years, slowly conducting heat upward from the hotter layers below, participating in geological processes so gradual that they unfold on timescales utterly disconnected from anything a human lifetime could witness. And yet, we are still in the shallow part of the story. We are still in the crust, which is itself only the thinnest outer shell, the skin stretched over something far larger and stranger. Beneath our feet, beneath the basements of buildings and the foundations of mountains, beneath the deepest valleys and the floors of the ocean, the planet extends downward for thousands of kilometers, through layers that transition from solid to partially molten, to liquid to solid again, through zones where the pressure is so immense that familiar materials behave in unfamiliar ways, where iron flows like water and stone bends like plastic, where the temperature exceeds that of the surface of the sun, and yet nothing melts because the weight of everything above holds it together. To understand what exists beneath the crust is to begin recognizing that the Earth is not a simple object, not a uniform sphere of rock, but a layered system of unimaginable complexity, each layer with its own composition, its own physical state, its own relationship to time and movement and heat. Perhaps the most unsettling realization is how little of this depth we have ever directly observed, and how much of what we know comes not from seeing, but from listening, from measuring the way seismic waves travel through rock after an earthquake, from observing how those waves speed up or slow down, or refract as they pass through boundaries between different materials, from reconstructing the planet's interior, the way a doctor might reconstruct the inside of a body using only the echoes of sound waves bouncing back from hidden organs. And what those echoes reveal is that the solid ground beneath us is only the beginning, the first thin layer in a structure that extends so far down and changes so dramatically with depth that standing on the surface and imagining the core is like standing at the edge of the ocean and trying to imagine the deepest trenches, except that the ocean, at its deepest point, is only 11 kilometers down, while the center of the Earth lies more than 6,000 kilometers below, a distance so vast that if you could somehow drill straight down at a constant speed of 1 meter per second, it would take you more than 2 months of continuous descent to reach it. The crust, when you begin to understand its true proportions, is almost disappointingly thin. We tend to imagine the solid ground as extending downward for vast distances, as if the mountains and valleys we see at the surface are merely the visible tips of structures that plunge deep into the planet, anchoring themselves in some fundamental bedrock that goes down and down until it becomes something else entirely. But the reality is stranger and more precarious than that. The crust, the entire rigid outer shell of the Earth, including the deepest roots of the highest mountains, the foundations of continents, the floors of ocean basins, is nowhere thicker than about 70 kilometers, and in most places, it is considerably thinner, sometimes as little as 5 kilometers beneath the ocean floor, a measurement so small relative to the planet's total radius that it almost vanishes when you try to visualize it at scale. If you were to construct a model of the Earth the size of a classroom globe, the crust would be represented by a layer of paint, or perhaps a coat of varnish, barely thick enough to catch the light. Beneath the continents, where the crust reaches its maximum thickness, it extends down perhaps 30 to 50 kilometers on average. Thicker beneath mountain ranges, where the roots of the peaks push deeper into the layers below. Thinner beneath plains and valleys, where the load is lighter and the structure less compressed. This continental crust is made primarily of lighter rocks, granites and their metamorphic relatives, rocks rich in silicon and aluminum, rocks that form through complex processes involving the melting and remelting of older materials, the differentiation of minerals by density and melting point, the slow accumulation of lighter elements at the top of the pile while heavier elements sank deeper. These are ancient rocks, some of them dating back billions of years, preserving in their crystalline structures a record of the early Earth, of a time when the planet's surface was still forming, still being bombarded by asteroids, still radiating heat from its violent birth. Beneath the oceans, the crust is dramatically thinner, rarely more than 7 or 8 kilometers from the seafloor, down to the boundary with the mantle below. This oceanic crust is younger, denser, made primarily of basalt, a dark volcanic rock that forms when magma rises from the mantle and cools quickly at the surface. It is created continuously at mid-ocean ridges, those underwater mountain ranges where tectonic plates pull apart and fresh molten rock wells up to fill the gap, solidifying into new crust that then spreads outward like a conveyor belt, moving away from the ridge at a rate of a few centimeters per year, eventually reaching the edges of ocean basins, where it collides with continental crust, and, being denser, sinks back down into the mantle in a process called subduction, completing a cycle that takes roughly 200 million years from birth to destruction. The oceanic crust is therefore impermanent, constantly being recycled, none of it older than about 200 million years, which in geological terms is relatively young, barely a 20th of the planet's total age. What strikes you when you consider these dimensions carefully is how superficial everything familiar actually is. The deepest ocean trench, the Mariana Trench, descends about 11 kilometers below sea level, which sounds profound until you realize that this is still well within the crust, still in the outermost skin of the planet, not even close to touching the mantle that lies below. The tallest mountain, Everest, rises nearly 9 kilometers above sea level, and its roots extend perhaps another 20 or 30 kilometers down. But even adding these together, even accounting for the full thickness of crust beneath the Himalayas, you are still describing a feature that represents less than 1% of the Earth's radius. The entire vertical range of the Earth's surface, from the deepest trench to the highest peak, amounts to about 20 kilometers, a distance you could drive in a car in 15 minutes. And yet it encompasses every landscape humans have ever known, every place we have ever stood, every mountain we have climbed, and every valley we have descended into. The crust, thin as it is, serves a particular function in the planet's architecture. It is rigid, brittle, unable to flow the way deeper materials can, and so it breaks rather than bends when subjected to stress. This brittleness is what gives us earthquakes, the sudden release of accumulated strain when rock fractures along fault lines, unable to accommodate the slow grinding motion of tectonic plates without eventually snapping. It is also what allows the crust to support mountains, to hold up the weight of continents. Because even though it is thin, it is strong in the way that an eggshell is strong, maintaining its shape through geometric distribution of forces rather than through sheer thickness. But unlike an eggshell, the crust is not uniform, not a single continuous shell, but a mosaic of separate plates, each one moving independently, driven by forces originating in the hotter, more fluid layers below. And it is precisely this thinness, this fragility, that makes the crust so different from what lies beneath it. Below this rigid shell, the planet transitions into something else entirely, into materials that behave according to different rules, that respond to pressure and heat in ways that solid rock at the surface never could. The boundary between crust and mantle is not gradual, not a smooth transition, but a sharp discontinuity, a place where the rock changes composition abruptly, where seismic waves suddenly accelerate because they are entering a denser, more rigid medium, where the temperature jumps and the pressure increases, and everything familiar about surface geology ceases to apply. This boundary has a name, the Mohorovičić discontinuity, usually shortened to the Moho, and it represents the first true threshold in our descent, the first moment when we leave behind the shallow world and enter the deep architecture of the planet. Standing on the surface, pressing your hand against stone, you are separated from that boundary by only a few dozen kilometers at most, and yet those kilometers might as well be an ocean, might as well be a void, because they represent a barrier that no human has ever crossed, that no drill has ever penetrated completely, that remains as remote and inaccessible as the surface of another planet. And beyond that barrier lies almost everything, almost the entire mass and volume of the Earth, waiting in silence and darkness, holding the world together in ways we have only begun to understand. As you descend deeper into the crust, past the fractured upper layers where water still seeps and temperatures still bear some relationship to the seasons above, you enter a realm where time itself begins to change character. Here, in what geologists call the deep crust, the rock has been sitting undisturbed for hundreds of millions of years, sometimes billions, compressed under the weight of everything above it, heated from below by the slow upward migration of thermal energy from the mantle, transformed gradually by pressure and temperature into forms that no longer resemble the sediments or volcanic flows from which they originated. This is basement rock, the ancient foundation upon which younger materials have accumulated, layer upon layer, like pages in a book that is still being written at the top while the bottom pages remain unchanged, their ink long dried, their paper yellowed with age, their words recording events so distant that they belong to a different Earth entirely. The deeper you go, the hotter it becomes. The temperature rises steadily, predictably, following what scientists call the geothermal gradient, and though the exact rate varies depending on local conditions, on whether you are beneath a tectonically active region or a stable craton, beneath thin oceanic crust or thick continental crust, the general pattern holds everywhere. At 10 kilometers down, the temperature might be 200 degrees Celsius, hot enough to boil water instantly, hot enough that any organic material would combust, and yet still far cooler than what awaits further below. At 20 kilometers, you might encounter temperatures exceeding 400 degrees, and at 30 kilometers, deep within the lower crust beneath mountain ranges, the rock might be heated to 600 degrees or more, temperatures at which certain minerals begin to soften, at which the rigid brittleness of surface rock gives way to something more plastic, more willing to deform slowly under sustained pressure, rather than fracturing suddenly the way shallow rock does. This heat is not coming from the sun. The sun warms only the outermost skin of the planet, the top few meters of soil and rock where daily and seasonal temperature fluctuations penetrate. Below that shallow zone, the temperature of the Earth is determined almost entirely by internal heat, heat left over from the planet's formation 4.5 billion years ago, heat generated continuously by the radioactive decay of unstable isotopes scattered through the rock, uranium, thorium, potassium, elements that break down slowly, releasing energy as they transform into lighter elements, a process that has been running since the Earth coalesced from the solar nebula and will continue for billions of years more, gradually cooling but never fully cold, never inert. This is a planet that generates its own warmth, that carries within itself the memory of its violent birth, and that warmth radiates outward constantly, moving through solid rock by conduction, seeping upward at a rate imperceptible to human senses, but measurable over geological time. What exists at these depths is rock that has never seen daylight, rock that formed deep underground and has remained there ever since, rock whose mineral grains grew slowly in darkness and pressure, interlocking with one another in patterns determined by the temperature and chemistry of their environment. Some of this rock is metamorphic, schist, gneiss, and fibrillite, formed when older rock was subjected to heat and pressure intense enough to rearrange its internal structure without melting it completely, a process that occurs over millions of years, grain by grain, molecule by molecule, as atoms migrate through solid crystal lattices, seeking more stable configurations. Other portions are igneous, granite or granodiorite, that crystallize slowly from molten magma deep underground, cooling over thousands of years, forming large interlocking crystals that give the rock its strength and durability. Crystals that record in their composition the chemical signature of the melt from which they formed, preserving information about conditions that existed when the continents were still assembling, when the surface of the Earth looked nothing like it does now. The age of this deep crustal rock is difficult to comprehend in any intuitive way. When geologists extract samples from deep boreholes and analyze the isotopes locked within their minerals, they are often dating events that occurred not millions but billions of years ago. Rock that formed when the Earth was less than half its current age, when the atmosphere was still toxic, when the continents were smaller and arranged in configurations that would be unrecognizable today, when no complex life existed anywhere on the planet. These rocks have survived multiple cycles of mountain building and erosion, have been buried and exhumed and buried again, have witnessed the assembly and breakup of supercontinents, the opening and closing of ocean basins, the rise and fall of entire mountain ranges, and through all of this they have remained largely intact, changing only slowly, adapting to new conditions by recrystallizing, by rearranging their minerals, but never losing their fundamental identity, never returning to the surface, never rejoining the rapid cycling of materials that characterizes the shallow Earth. At the base of the crust, 20 or 30 or even 70 kilometers down in places where the crust is thickest, the conditions become extreme enough that rock begins to approach its melting point, not melting entirely, but softening, becoming ductile, capable of flowing very slowly under sustained stress. This is where the crust, despite being classified as solid, begins to behave in ways that challenge our surface world understanding of what solid means. Apply enough pressure for enough time, and even rock will bend, will flow, will fold into complex shapes without breaking, deforming plastically the way warm wax deforms when you press on it, except that the timescale is not seconds, but millions of years, and the forces involved are not the pressure of a thumb, but the weight of entire mountain ranges, the collision of continents, the slow grinding motion of tectonic plates that move at the speed of growing fingernails, but carry the mass of subcontinents with them. And just below this, separated by the thinnest of boundaries, lies something fundamentally different, something that is no longer crust at all, but the first layer of the mantle, a realm where the rock is denser, hotter, structured differently at the atomic level, governed by physical laws that become increasingly strange the deeper you go, increasingly removed from anything the human body could survive, or the human mind easily picture. And yet, it is all there, has always been there, will remain, there long after the mountains have eroded and the oceans have shifted and everything recognizable about the current surface of the Earth has changed beyond recognition. There is a zone just above the boundary that separates crust from mantle, where the character of rock begins to shift in subtle ways that would be invisible to the eye, but are unmistakable in the behavior of seismic waves passing through. Here, at depths approaching the moho, the temperature has climbed to 700, 800, sometimes 900 degrees Celsius, and the pressure exerted by the overlying column of rock is measured in tens of thousands of atmospheres, conditions so far removed from the surface environment that the minerals stable at sea level cannot exist here, cannot maintain their crystalline structures under such stress. Instead, the rock is composed of high-pressure variants of familiar minerals, denser forms that pack more atoms into less space, that respond to the crushing weight above them by reorganizing their internal architecture, by shedding water molecules that were incorporated into their crystal lattices when they formed in cooler, shallower conditions, by transforming incrementally into phases that can only exist where the Earth's weight is sufficient to force atoms closer together than they would ever arrange themselves under normal circumstances. This is still the crust, technically, still part of the rigid outer shell. But it is the lower crust, the foundation layer, the part that bears the full accumulated load of everything above it and transmits that weight downward to the mantle below. The rock here has been sitting under this pressure for so long that it has adapted to it, has recrystallized into forms that are stable under these conditions, and yet it remains brittle in the sense that it can still fracture, can still break along planes of weakness if the stress becomes too great, or if it is subjected to forces it was not designed to resist. Deep earthquakes, rare but measurable, occasionally occur at these depths, their tremors propagating upward through the crust to shake the surface world, a reminder that even here, in the deep foundation of the planet, the rock is not entirely static, not entirely at rest, but exists in a state of constant subtle strain, responding to the slow shifting of tectonic plates, to the rise and fall of magma plumes from below, to the gradual redistribution of mass as continents drift and ocean basins open and close. The composition of the lower crust varies depending on where you are, but in general, it tends to be richer in iron and magnesium than the upper crust, denser, darker, made of rocks like gabbro and granulite that formed from magmas or underwent metamorphism at high temperatures and pressures. These are the kinds of rocks that, if they were ever brought to the surface, by tectonic uplift, by the erosion of overlying layers, by the deep excavation of mountain roots, would appear unremarkable to the untrained eye, just dark stone, heavy and hard, but which to a geologist represents something profound, something that formed in conditions so extreme that finding them exposed at the surface is like finding a fragment of the deep ocean floor on a mountaintop, evidence that the planet's interior is not fixed but mobile, that what is deep can become shallow, and what is shallow can be dragged down into the depths, that the Earth recycles its materials on timescales so long that entire mountain ranges can rise and erode away in the time it takes for a piece of lower crust to complete a single cycle from depth to surface and back again. What you begin to sense as you approach the base of the crust is that the familiar world is ending. The rocks here are the last that were formed by processes we would recognize as crustal, partial melting of older materials, intrusion of magma from below, metamorphism under high pressure and temperature, but still within the realm of solid-state reactions, still governed by the chemistry and physics of the crust. Below this, across the moho, everything changes. The mantle is not just deeper crust, not just a continuation of the same materials under more extreme conditions, but a fundamentally different substance, made of different minerals, responding to pressure and heat in different ways, participating in different geological processes. The moho is not a place where the temperature suddenly spikes or the pressure suddenly increases. Both of those continue to rise smoothly with depth, but rather a place where the composition shifts, where the rock on one side of the boundary is chemically and mineralogically distinct from the rock on the other side. A transition so sharp that seismic waves passing through it change speed within a distance of just a few meters. This boundary was discovered not by drilling or by direct observation. No one has ever seen the moho. No sample has ever been retrieved from it, but by listening to earthquakes. In 1909, a Croatian seismologist named Andrija Mohorovičić noticed that seismic waves from earthquakes traveled faster after they had penetrated below a certain depth, and he correctly interpreted this as evidence of a discontinuity, a place where the waves were entering a denser, more rigid material. The depth of this boundary could be calculated from the travel times of the waves, and when geologists around the world began making similar measurements, they found that the moho existed everywhere, that it was a global feature separating the crust from the mantle beneath it, that it lay at different depths in different places but was always present, always marking the same fundamental transition. It is one of the great invisible structures of the planet, a boundary that defines the architecture of the entire Earth, but which exists entirely beyond human reach, known only through inference, through the analysis of vibrations that have passed through it, and return to tell us something about what lies below. Standing at the surface, you are always standing above this boundary, separated from it by at least 5 kilometers, and usually much more. And yet, it is this boundary, more than anything else, that defines the limits of the world you know. Everything above the moho is crust, thin, brittle, chemically evolved, the product of billions of years of differentiation and recycling. Everything below it is mantle, thicker, denser, more primitive, closer in composition to the material from which the entire planet originally formed. The crust is where we live, where mountains rise and rivers flow and continents drift slowly across the surface. But the mantle is where the energy comes from, where the heat originates, where the slow, churning convection occurs that drives the motion of tectonic plates and shapes the surface from below. Invisible, but absolutely essential, the engine beneath the skin. And now, having descended through the crust from the surface to the moho, having passed through soil and bedrock and deep basement rock, and the high-temperature zone at the base of the crust, we arrive at the threshold, the edge of the known world, the boundary beyond which lies a volume of rock so vast and so remote from human experience that it might as well be another planet, except that it is not another planet. It is this planet. It is here, directly beneath you, extending downward for thousands of kilometers, waiting in silence. Cross the moho, descend just a few meters below that invisible line, and you are no longer in the crust. You are in the mantle, and though the transition happens over a distance shorter than the height of a room, the change is absolute. The rock here is not granite or basalt, not the chemically evolved materials that make up the continents and ocean floors, but peridotite, a dense greenish stone composed primarily of olivine and pyroxene, minerals rich in magnesium and iron, minerals that form the bulk of the Earth's interior and represent, in many ways, the planet's original composition, the material from which everything else was derived. When the Earth was young and still molten, lighter elements rose to the surface and eventually formed the crust, but the mantle retained the heavier, more primitive chemistry, and it has remained fundamentally unchanged in composition for billions of years, a reservoir of ancient material that has been slowly stirred and circulated by convection, but never separated into the distinct chemical layers that characterize the crust above. The density increases sharply here. Crustal rock, even at its base, has a density of about 2.8 or 2.9 grams per cubic centimeter, but mantle rock is denser, around 3.3 grams per cubic centimeter, heavier because it contains more iron, because its minerals are packed more tightly, because the pressure at these depths compresses everything into more compact forms. This difference in density is part of what makes the boundary so distinct to seismic waves. The waves are entering a medium where atoms are closer together, where sound travels faster, where the rock is more rigid despite being hotter. It is also this density difference that drives much of the planet's internal dynamics, because when hot mantle rock rises toward the surface, it can partially melt, and the melt that forms is lighter than the solid residue, and that lighter melt rises further, eventually reaching the surface as lava or solidifying at depth as intrusive igneous rock, gradually building the crust over geological time, while the dense residue sinks back down, returning to the mantle, maintaining the separation between light crust and heavy mantle that defines the Earth's layered structure. The temperature here, just below the moho, might be somewhere between 800 and 1000 degrees Celsius, hot enough to glow if you could see it, hot enough to vaporize any organic material instantly. And yet the rock is solid, not molten, not even close to melting, because the pressure is so immense that it raises the melting point far above what it would be at the surface. At atmospheric pressure, olivine melts at around 1300 degrees, but at the pressures found in the upper mantle, tens of thousands of times greater than atmospheric pressure, the melting point rises to 1800 degrees or more, and so the rock remains solid even though it is hotter than a blacksmith's forge, hotter than the flames of a wood fire, locked into a crystalline state by the sheer weight of everything above it, unable to melt unless the pressure is somehow reduced or the temperature raised even higher. And yet, Despite being solid, this rock is not static. It moves, flows, deforms plastically over geological time, not because it is liquid, but because at these temperatures and pressures, solid rock behaves differently than it does at the surface. The atoms in the crystal lattices vibrate more intensely, have more energy, and under sustained stress, they can migrate, can slip past one another, can rearrange themselves slowly, allowing the rock as a whole to change shape without fracturing, to flow the way glacial ice flows, solid but mobile, rigid on short timescales but ductile over millions of years. This is the fundamental difference between the crust and the mantle. The crust is brittle, breaks when stressed, behaves like a rigid shell, while the mantle, despite being solid, behaves over long periods like a very viscous fluid, capable of convection, capable of circulating heat and material over vast distances, rising in some places and sinking in others, driven by temperature differences and density contrasts that create currents as slow and inexorable as the movement of continents themselves. The upper mantle, which extends from the Moho down to a depth of about 400 kilometers, is where much of this circulation occurs. Hot rock rises from deeper in the mantle, moving upward at rates measured in centimeters per year, ascending for millions of years until it reaches the base of the crust, where it spreads horizontally, cooling as it goes, eventually becoming dense enough to sink back down, descending into the interior to be reheated and rise again in a cycle that has been running for billions of years and will continue for billions more. This convection is what drives plate tectonics, what causes continents to drift and ocean basins to open and close, what builds mountains and generates earthquakes and fuels volcanic eruptions. Everything that happens at the surface, every earthquake, every volcanic arc, every mid-ocean ridge, every subduction zone, is ultimately powered by the slow churning of the mantle below, by the heat escaping from the Earth's interior, by the gravitational instabilities that arise when hot material is less dense than cold material and begins to rise while cold material sinks. The olivine crystals that make up most of the upper mantle are arranged in interlocking grains, much like the crystals in granite or basalt, but the conditions under which they formed are so different that the rock behaves according to its own rules. Olivine is a silicate, built from silicon and oxygen tetrahedra, linked by magnesium and iron atoms, and its crystal structure is stable across a wide range of temperatures and pressures, which is why it dominates the upper mantle from the Moho all the way down to about 400 kilometers. Below that depth, the pressure becomes great enough to force the olivine to transform into a denser polymorph called wadsleyite, and deeper still, it transforms again into ringwoodite, and then finally into a completely different set of minerals as you approach the lower mantle. But here, in the upper mantle, olivine reigns, green and dense and capable of flowing over geological time, the fundamental substance of the planet's interior. What you realize, as you imagine descending through this realm, is that the mantle is not a minor component of the Earth, not a thin layer beneath the crust, but the dominant structure, the bulk of the planet's volume and mass. The mantle extends from the Moho, which lies at most a few dozen kilometers below the surface, all the way down to a depth of 2,900 kilometers, accounting for roughly 84% of the Earth's total volume and 67% of its mass. The crust, by comparison, is a rounding error, a thin coating that barely registers in the planet's overall structure. To understand the Earth is not to understand the crust, which is merely the interface, the boundary layer, the skin, but to understand the mantle, which is the substance, the engine, the slow-moving ocean of solid rock that has been shaping the surface from below since the planet first cooled enough to develop a solid shell. Imagine rock flowing the way water flows, except that the flow is so slow you could watch it for 1,000 human lifetimes and never see it move, never detect the slightest shift in position, never perceive any change at all, and yet it is moving, has been moving, will continue moving for as long as the Earth remains hot enough to drive the process. This is what happens in the upper mantle, in the 100 or 200 kilometers immediately below the Moho, where the temperature and pressure combine to create conditions under which solid crystalline rock behaves over sufficient spans of time, like an extraordinarily viscous fluid, deforming plastically, flowing in great slow currents that rise and fall and circulate heat from the deep interior toward the surface. The viscosity of this flowing rock is almost unimaginable, billions of times more viscous than honey, trillions of times more viscous than water, and yet it is not infinite, not locked in place, and so it moves, creeping forward at velocities measured in centimeters per year, sometimes faster, sometimes slower, but always in motion, always responding to the temperature gradients and density contrasts that create buoyancy forces strong enough to overcome the rock's resistance to flow. This motion is called mantle convection, and it is the fundamental engine that drives everything we see happening at the surface. When rock deep in the mantle is heated, by radioactive decay, by residual heat from the planet's formation, by heat conducted upward from the even hotter core below, it expands slightly, becomes less dense than the cooler rock surrounding it, and begins to rise, not quickly, not dramatically, but steadily, ascending through the mantle like a thermal plume rising through thick syrup, carrying heat upward from depth. As it rises, it cools very slowly, losing heat to the rock around it, but the cooling happens over such long timescales that the rising plume can travel hundreds of kilometers before it equilibrates with its surroundings. When it finally reaches the base of the lithosphere, the rigid outer shell of the Earth that includes the crust and the uppermost mantle, it spreads horizontally, unable to rise further because the lithosphere is too cold and rigid to allow penetration. And so the hot mantle rock flows sideways, moving beneath the tectonic plates like a conveyor belt, cooling as it goes, gradually becoming denser until eventually it becomes heavy enough to sink, to descend back into the interior, completing a cycle that can take 100 million years or more from start to finish. The tectonic plates themselves, the fragments of lithosphere that make up the Earth's surface, carrying continents and ocean basins slowly across the planet, are not actively driving their own motion, but are being carried passively by these mantle convection currents below them, like rafts floating on a river, moved by forces they do not generate. Where mantle rock rises, the lithosphere is pulled apart, creating rifts and spreading centers where new oceanic crust forms. Where mantle rock sinks, the lithosphere is dragged downward, creating subduction zones where old oceanic crust descends back into the mantle to be recycled. The entire system is coupled, interconnected, such that the slow flow of the mantle dictates the arrangement of continents, the location of mountain ranges, the distribution of earthquakes and volcanoes, all of it emerging from the deep circulation of solid rock that most people never think about, never imagine, never consider as they walk across the surface of a seemingly stable planet. The speed of this convection is determined by the viscosity of the mantle rock, by the temperature difference between hot rising material and cold sinking material, and by the depth over which the convection occurs. Measurements of plate velocities at the surface, which can be made very precisely using GPS and satellite observations, show that plates move at rates between 1 and 10 centimeters per year, about as fast as fingernails grow, and this surface velocity reflects the underlying mantle flow rates, the speed at which hot rock rises and cool rock sinks in the slow churning below. 10 centimeters per year sounds trivial, barely perceptible, but sustained over 100 million years it amounts to 10,000 kilometers, enough to carry a continent from one side of the planet to the other, enough to open an entire ocean basin, enough to assemble a supercontinent or tear one apart. Geological time transforms trivial velocities into planetary-scale displacements, makes the impossible routine, turns the static world of everyday experience into a dynamic system in constant, relentless motion. What drives this motion, ultimately, is heat. The mantle is hotter at depth than it is near the surface, and this temperature gradient creates instability because hot material is less dense and wants to rise while cold material is denser and wants to sink. In a static solid, these density differences would simply exist, locked in place, unable to act. But in the mantle, where the rock can flow over geological time, the density differences drive motion, generate circulation, allow the system to transport heat from the interior outward toward the surface much more efficiently than conduction alone ever could. If the Earth had no mantle convection, if heat could only escape by conduction through static rock, the planet would cool far more slowly, would retain its internal heat for trillions of years, and the surface would be geologically dead, frozen, unchanging. But because the mantle convects, because hot rock rises and cold rock sinks, heat is carried upward continuously, released at the surface through volcanism and seafloor spreading, and the planet remains geologically active, continues to reshape its surface, continues to evolve even after 4.5 billion years. The rock that participates in this convection is not molten, is not even partially molten except in rare localized zones where the pressure drops or the temperature spikes. But it flows nonetheless, its crystal grains deforming slowly through processes called dislocation creep and diffusion creep, mechanisms by which individual atoms can migrate through the crystal lattice, can rearrange themselves in response to applied stress, allowing the grain boundaries to slide past one another, allowing the bulk rock to change shape without breaking. This is solid-state flow, fundamentally different from the flow of a liquid, slower, more constrained, requiring much larger forces to drive, but still capable of producing motion, still capable of transporting material over vast distances given enough time. The timescale of this flow is matched to the timescale of geological processes. Mountain building takes millions of years. Ocean basins open and close over hundreds of millions of years. And the mantle convection that drives these processes operates on the same deep, patient timescale, never hurrying, never accelerating beyond a few centimeters per year, but never stopping either, never pausing, always moving, always circulating, always working to redistribute heat and mass within the planet. Beneath the continents, the mantle flow is disrupted by the thick roots of cratons, the ancient stable cores of continents that extend deeper than normal lithosphere, acting like keels on a ship, anchoring the continents and deflecting the mantle currents around them. Beneath the oceans, where the lithosphere is thinner and younger, the mantle flow is more direct, more vigorous, driving the creation of new crust at mid-ocean ridges and the destruction of old crust at subduction zones, with a mechanical efficiency that has been operating since plate tectonics began, perhaps as far back as 3 billion years ago, perhaps more recently, the exact timing still debated, still uncertain, but the process itself unmistakable, written into the structure of the ocean floor, into the magnetic stripes that record reversals of the Earth's magnetic field, into the age distribution of seafloor rocks that get progressively older as you move away from the ridges and younger as you approach them. And all of this motion, all of this slow, planetary scale circulation happens in darkness, happens in rock so hot you could not touch it without vaporizing, happens under pressures that would crush any vessel humans could build, happens in a realm that has never been directly observed and never will be, known only through the tremors that pass through it, through the heat that escapes from it, through the way it shapes the surface from below, invisibly, patiently, moving continents across the face of the Earth with the same inexorable momentum that moves glaciers down mountain valleys, except slower, vastly slower, operating on a timescale so extended that it makes human history, all of human history, appear as a single brief moment in a process that has been unfolding for eons and will continue unfolding for eons more. There is a layer within the upper mantle, beginning at a depth of perhaps 80 or 100 kilometers below the surface and extending downward for another 100 kilometers or so, where the rock becomes noticeably softer, more compliant, more willing to deform under stress than the material immediately above or below it. This zone is called the asthenosphere, from the Greek word for weak, though weak is perhaps misleading because the rock here is not fragile, not brittle, not structurally compromised in any way that would cause it to crumble or fail. Rather, it is weak only in the sense that its resistance to flow is lower than elsewhere, that its viscosity is reduced, that it responds to applied forces by deforming more readily, flowing more easily, accommodating motion with less resistance. The asthenosphere is not a distinct layer in the way the crust is a distinct layer, not separated from the mantle above or below it by any sharp compositional boundary, but rather a zone defined by its physical properties, by the way it behaves under the temperature and pressure conditions that exist at these depths. What makes the asthenosphere different is temperature. At depths of 100 to 200 kilometers, the rock is hot enough, perhaps 1300 to 1400 degrees Celsius, that it approaches its melting point, not exceeding it, not turning liquid, but getting close enough that the solid crystalline structure begins to soften significantly, begins to lose some of its rigidity, begins to flow more easily than cooler rock at shallower or deeper levels. In some regions, particularly beneath mid-ocean ridges where hot mantle material is rising toward the surface, the asthenosphere may contain small amounts of partial melt, tiny pockets or films of liquid rock distributed along grain boundaries, just 1 or 2% by volume, not enough to make the rock as a whole liquid, but enough to lubricate the crystal grains, to allow them to slide past one another more freely, to reduce the effective viscosity of the bulk material. This partial melting occurs because even a small reduction in pressure, or a slight increase in temperature, or the presence of volatiles like water or carbon dioxide, can lower the melting point of mantle rock enough that some fraction of it begins to melt, while the rest remains solid, creating a mush, a two-phase mixture that behaves mechanically very differently from pure solid rock. The asthenosphere is where the tectonic plates decouple from the deeper mantle, where the rigid lithosphere above, which includes the crust and the uppermost mantle, lock together into a single coherent shell, stops being rigidly connected to the convecting mantle below. The plates do not move because they are being dragged across a fixed surface, but because they are floating on, or more accurately embedded in, the asthenosphere, which flows beneath them and around them, allowing them to slide horizontally, to rotate, to diverge at spreading centers and converge at subduction zones, all without requiring the entire mantle to move in lockstep with the surface. The asthenosphere acts as a lubricating layer, a zone of reduced coupling, a mechanical buffer between the cold, rigid shell of the lithosphere and the hotter, more vigorously convecting mantle beneath. Without this layer, without this zone of weakness, plate tectonics as we understand it might not be possible, because the plates would be mechanically locked to the deeper mantle, unable to move independently, unable to slide past one another, unable to subduct or to rift apart. The thickness of the asthenosphere varies depending on where you are. Beneath mid-ocean ridges, where the mantle is hottest and rising most actively, the asthenosphere can extend almost to the base of the crust, reducing the lithosphere to a very thin layer, sometimes only a few kilometers thick, young and hot, and barely rigid enough to qualify as a plate. Beneath old, cold ocean basins far from spreading centers, the lithosphere thickens as it cools, and the top of the asthenosphere descends to greater depths, perhaps 150 kilometers or more below the surface. Beneath continents, particularly beneath old stable cratons, the lithosphere can be even thicker, extending 200 kilometers down or more, and the asthenosphere begins only below that depth, its reduced viscosity still present, but buried deeper, insulated from the surface by a thick layer of cold, rigid mantle that has been cooling for billions of years and has become as much a part of the continent as the crust itself. What you sense as you imagine descending through the asthenosphere is that the Earth's interior is not a simple stack of uniform layers, but a dynamic system where the boundaries between layers shift with temperature and pressure, where the properties of rock change gradually with depth, where the distinction between solid and fluid becomes increasingly ambiguous the hotter and deeper you go. The asthenosphere is solid in the sense that it has a crystal structure, that it can transmit seismic shear waves, that it does not behave like a liquid on short timescales, and yet it is also fluid in the sense that it flows, that it convects, that it deforms continuously under its own weight and under the forces exerted by the moving plates above. The boundary between the lithosphere and the asthenosphere is not a sharp line, but a gradual transition, a zone where the rock progressively loses its rigidity, where the timescale over which it can sustain stress without deforming becomes shorter and shorter, where what was solid on human timescales becomes fluid on geological timescales. The temperature in the asthenosphere is high enough that the olivine crystals making up most of the rock are vibrating intensely, their atoms oscillating around their equilibrium positions with enough energy that defects in the crystal lattice, dislocations, vacancies, grain boundaries become pathways for deformation, for the slow migration of atoms from one position to another, for the rearrangement of crystal structures under applied stress. This is not melting, not the breakdown of crystalline order into liquid disorder, but something subtler, a kind of solid-state plasticity where the material retains its structure but loses its resistance to flow, where forces that would cause brittle fracture in cooler rock instead cause slow creep, gradual deformation, the kind of motion that can move continents but cannot ring a bell or shatter a window. The viscosity of the asthenosphere is perhaps 100 times lower than the viscosity of the lithosphere above it, and 100 times higher than the viscosity of water, meaning it occupies a middle ground between true solid and true liquid, between static and mobile, between permanent and transient. Seismic waves traveling through the asthenosphere slow down slightly compared to waves traveling through the lithosphere above, or the deeper mantle below, and this slowing is how geologists first identified the layer, how they mapped its extent and depth, by observing that certain earthquake waves arrived at seismometers slightly later than expected, indicating they had passed through a zone where the wave velocity was reduced. This low-velocity zone, as it is sometimes called, is not present everywhere. Beneath very old, very cold lithosphere, it may be absent or barely detectable, but beneath most of the ocean floor and beneath tectonically active continental regions, it is there, a global feature, a fundamental component of the Earth's internal structure, the layer that allows the surface to move, that permits plate tectonics to operate, that decouples the rigid outer shell from the convecting interior. And what this means, as you continue descending in imagination through this softened zone, is that the Earth is not simply getting denser and hotter with depth, but is also changing in character, transitioning from materials that behave according to familiar mechanical laws into materials that operate in stranger regimes, where solids flow and pressures compress atoms into unfamiliar arrangements and temperatures climb toward values that would vaporize any substance at the surface. And yet the rock remains intact, remains functional, remains part of the system that has been regulating the planet's heat loss and shaping its surface for billions of years, patient and tireless and utterly indifferent to the brief flicker of human observation, trying to comprehend it from above. Below the asthenosphere, as you descend past 200 kilometers, past 250, the rock becomes rigid again, not cooler, but denser, compressed by the accumulating weight above until its resistance to flow increases despite the rising temperature, until the mantle regains a kind of strength it had lost in the softened zone above. This is the deeper portion of the upper mantle, extending downward toward 400 kilometers, then beyond, a vast region where convection continues, but at higher viscosities, where the circulation of rock becomes slower, more labored, more constrained by the extreme pressures that now measure in the hundreds of thousands of atmospheres, pressures so far beyond anything experienced at the surface that the very concept of pressure begins to lose its intuitive meaning, becomes just a number, an abstraction describing forces that would collapse any container, compress any material, transform familiar substances into forms that could only exist under these buried conditions. The temperature continues its steady climb, reaching 1500 degrees Celsius, then 1600, then 1700, climbing toward values that seem impossibly hot until you remember that the rock remains solid, locked into crystalline structures by pressures that overwhelm the thermal energy trying to disorder it, preventing melting through sheer force, through the weight of hundreds of kilometers of overlying stone pressing down with a persistence that cannot be escaped or evaded. At these depths, heat moves primarily by convection, by the bulk motion of rock carrying thermal energy with it as it rises or sinks. And though conduction still occurs, heat still diffuses from hotter regions to cooler ones through direct atomic contact. The rate of conduction is slow compared to the rate at which convection can transport heat. and so the mantle remains well mixed thermally, avoiding the extreme temperature gradients that would develop if convection were not present, maintaining a relatively smooth increase in temperature with depth, rather than sharp discontinuities or thermal boundary layers that would isolate the deep interior from the surface. The convection cells operating at these depths are enormous, spanning hundreds or even thousands of kilometers horizontally, rising and sinking over timescales of tens or hundreds of millions of years. Their motion detected not by watching them move, they are far too slow for that, far too deeply buried, but by analyzing the distribution of earthquake hypocenters, the pathways of seismic waves, the subtle variations in the pull of gravity at the surface that hint at density anomalies deep below, at places where cold dense rock is sinking or hot buoyant rock is rising. These observations, pieced together from decades of data collection, from thousands of earthquakes recorded by global seismometer networks, reveal that the mantle is not circulating as a single unified cell, but as a complex pattern of multiple cells, some large and some smaller, some extending through the entire mantle from core to crust, and others confined to the upper mantle, their boundaries shifting over geological time, responding to changes in the distribution of heat sources, to the locations of subducting slabs, to the cooling of the planet as a whole. Some of these convection currents are driven by slabs of cold oceanic lithosphere that have descended into the mantle at subduction zones, heavy and dense because they are cooler than the surrounding rock, sinking under their own weight, pulling the rest of the tectonic plate behind them, generating most of the force that drives plate motion at the surface. These slabs can be traced seismically, their cold, dense structure causing seismic waves to travel through them faster than through the hotter mantle around them, creating what seismologists call fast anomalies, shadows of subducted plates that penetrated deep into the earth millions of years ago, and are still sinking, still descending, still en route to depths where they will eventually warm up and lose their density contrast and merge with the surrounding mantle, becoming indistinguishable from the material that has been circulating there for billions of years. Some slabs appear to stall at a depth of about 660 kilometers, pausing at a boundary where the mantle undergoes a phase transition, where the minerals transform into denser polymorphs, creating a change in buoyancy that temporarily halts the descent. But eventually, most slabs seem to overcome this barrier and continue sinking, reaching the lower mantle, perhaps even descending all the way to the core mantle boundary, nearly 3,000 kilometers below the surface. Other currents are driven by hot plumes rising from deep in the mantle, possibly from the core mantle boundary itself, where heat from the liquid iron core below is absorbed by the overlying mantle rock, creating thermal instabilities that detach and rise like bubbles through honey, ascending for hundreds of millions of years, eventually reaching the base of the lithosphere where they spread out, sometimes penetrating through weak spots to produce volcanic hotspots at the surface. Hawaii, Iceland, Yellowstone, places where volcanism occurs far from plate boundaries, isolated centers of activity that remain roughly stationary as the tectonic plates move over them, leaving trails of progressively older volcanoes behind, like breadcrumbs marking the plate's motion. The plumes themselves, if they exist as coherent rising columns, this is still debated among geophysicists, still uncertain from the seismic data, would be hundreds of kilometers in diameter, rising at velocities of perhaps 10 or 20 centimeters per year, faster than the general background convection, but still slow by any everyday standard, still taking millions of years to traverse the mantle's depth. The scale of these circulation patterns is difficult to hold in mind. A single convection cell might span half the circumference of the Earth, rising beneath the Pacific Ocean and sinking beneath Asia, carrying rock upward on one side of the planet and downward on the other, completing a full cycle in 100 million years, recycling material between surface and depth, in a mixing process that has been operating since the planet's early history, homogenizing the mantle's composition, preventing it from separating completely into unmixed layers, ensuring that heat generated in the deep interior eventually reaches the surface and escapes into space. Without this convection, without this slow stirring, The Earth would retain its primordial heat far longer, would remain geologically active for trillions of years, but would never develop plate tectonics, never reshape its surface continually, never sustain the kind of dynamic crustal recycling that may be unique to our planet among the rocky worlds of the solar system. The rock participating in this circulation is still primarily olivine in the upper mantle, but as you descend toward 400 kilometers depth, the pressure becomes great enough to force the olivine to transform into wadsleyite, a denser polymorph with the same chemical composition, but a different crystal structure, one that packs the atoms more tightly, that responds to the crushing force by reorganizing into a more compact form. This transformation happens abruptly at a specific depth, creating a seismic discontinuity where wave velocities suddenly increase, where the mantle's properties change in a way that has nothing to do with composition or temperature, but everything to do with the atomic level response to pressure. And deeper still, at about 520 kilometers, wadsleyite transforms into ringwoodite, another even denser polymorph, and the process repeats, the rock compressing itself step by step, finding ever more efficient ways to pack its constituent atoms into smaller volumes, responding to the relentless pressure by becoming denser, heavier, more tightly bound. And through all of this, through the phase transitions and the convection and the slow circulation of material over planetary distances, the mantle continues its ancient work, transporting heat, driving tectonic motion, reshaping the surface imperceptibly from below, operating according to physical laws that care nothing for observation, that function identically whether witnessed or not, that have been running since before the Earth had oceans or an oxygen atmosphere or anything resembling the world we know, and will continue running until the planet cools sufficiently for convection to cease, an event that lies billions of years in the future, so distant that the sun itself will have changed beyond recognition before the mantle finally goes still. At a depth of approximately 660 kilometers, something fundamental changes. The minerals that have dominated the mantle from the surface down to this point, olivine and its high-pressure polymorphs, wadsleyite and ringwoodite, can no longer sustain their crystal structures under the immense pressures that exist here. Pressures now exceeding 200,000 atmospheres, forces so great that the atomic bonds holding the crystals together must reorganize completely, must abandon their familiar silicate frameworks and adopt entirely new configurations. The ringwoodite breaks down, its silicon-oxygen tetrahedra collapsing into denser arrangements, and from this transformation emerge new minerals with names that sound almost alien. Bridgmanite, the most abundant mineral in the Earth despite being forever hidden from direct view, and ferropericlase, an oxide of magnesium and iron that exists nowhere at the surface but dominates the deep interior. This is the boundary between the upper mantle and the lower mantle, a transition as significant in its way as the moho, marking the entrance into a realm where the very substances making up the planet shift into forms that can only exist under the crushing weight of hundreds of kilometers of overlying rock. The lower mantle is vast beyond easy comprehension, extending from 660 kilometers down to nearly 2,900 kilometers, accounting for more than half of the Earth's total volume, a region so large that you could fit all of the crust and all of the upper mantle into it and still have room left over. To descend through the lower mantle at the same 1 meter per second we have been imagining would take more than 3 weeks of continuous downward motion, 3 weeks of passing through rock that is hotter than molten lava, denser than any material you have ever held, compressed by pressures that reach into the millions of atmospheres, and yet still fundamentally solid, still capable of transmitting seismic shear waves, still participating in convection, but on timescales even longer than the upper mantle, circulating with a ponderous slowness that makes the already glacial pace of upper mantle convection seem almost rapid by comparison. Bridgmanite, which makes up about 70% of the lower mantle's volume, has a crystal structure fundamentally different from the olivine that dominates the upper mantle. Instead of isolated silicon-oxygen tetrahedra linked by metal ions, Bridgmanite arranges its atoms into a perovskite structure, a densely packed lattice where silicon sits at the center of octahedra rather than tetrahedra, surrounded by 6 oxygen atoms instead of 4, achieving a more compact geometry that can withstand the extreme pressures without collapsing. This mineral has only been synthesized in laboratories under controlled high-pressure conditions, never found naturally at the surface, because it becomes unstable when the pressure is released, transforming back into less dense forms as soon as it rises above the 660-kilometer boundary. And so everything we know about its properties has been learned through experiments that recreate deep Earth conditions in tiny capsules subjected to pressures generated by diamond anvil cells. Devices that can compress samples to millions of atmospheres while simultaneously heating them to thousands of degrees, allowing scientists to probe the behavior of materials under conditions that exist nowhere on Earth's surface, but everywhere in its deep interior. The temperature at the top of the lower mantle is perhaps 1800 degrees Celsius, and it rises steadily as you descend, climbing toward 2000 degrees at 1,000 kilometers depth, then 2500 degrees deeper still, following a temperature profile that is controlled by the rate at which heat is being transported upward by convection, and the rate at which it is being generated by radioactive decay within the rock itself. The heat capacity of the lower mantle is enormous. The sheer mass of material involved means that even small changes in its average temperature represent staggering amounts of thermal energy, enough to power all of human civilization for millions of years. And yet this heat is trapped, imprisoned by the insulating layers above, escaping only slowly through the patient process of convection, rising centimeter by centimeter, year by year, taking hundreds of millions of years to travel from the bottom of the lower mantle to the top, transferring its energy to the upper mantle, which in turn transfers it to the lithosphere, which finally releases it to the surface through volcanism and seafloor spreading and the general cooling of the crust. The viscosity of the lower mantle is perhaps 10 to 100 times higher than the viscosity of the upper mantle, meaning that the rock here flows even more slowly, deforms even more reluctantly, resists convection with even greater stubbornness, and yet it still flows, still circulates, still participates in the grand overturning that characterizes the Earth's interior. Some geophysicists believe that the lower mantle convects separately from the upper mantle, that the 660-kilometer discontinuity acts as a partial barrier to circulation, dividing the mantle into 2 distinct convective systems that exchange material only slowly, only occasionally, creating a layered convection pattern, where the upper mantle churns more vigorously, while the lower mantle circulates more sluggishly beneath it. Others believe that the convection extends through the entire mantle, that subducting slabs penetrate all the way down to the core mantle boundary, and that mantle plumes rise all the way up from the base of the mantle to the surface, creating a whole mantle convection system where material mixes between upper and lower regions over very long timescales, hundreds of millions of years per cycle, but still fundamentally connected, still part of a single unified circulation. The evidence for either model comes from seismic tomography, a technique that uses earthquake waves to create 3-dimensional images of the mantle's internal structure, mapping variations in seismic velocity that correlate with variations in temperature and composition. These maps show cold slabs of subducted lithosphere penetrating deep into the lower mantle, visible as fast seismic anomalies that can be traced from the surface down to great depths, sometimes appearing to pile up at the base of the mantle, sometimes seeming to stagnate at the 660-kilometer boundary. The observation's complex and ambiguous enough that both models remain viable, both supported by some data and contradicted by other data, the truth perhaps lying somewhere. Between the 2 extremes, a mantle that circulates as a whole but with complications, with barriers that are permeable but not transparent, with mixing timescales that vary depending on location and on the vigor of convection at any given time. What becomes clear as you imagine descending through this enormous volume of rock, through 1,000 kilometers and then 2,000, through depths that now measure in significant fractions of the Earth's radius, is that the human intuition for scale begins to fail entirely. The crust was thin, the upper mantle was already vast, but the lower mantle dwarfs both, extends so far down that the surface seems almost irrelevant, a distant boundary that barely affects conditions at these depths, where the dominant influence is not the thin, cold layer above, but the hot, liquid core below, where the pressure is determined not by the weight of the crust or the lithosphere, but by the accumulated mass of the entire mantle pressing down from above, where the temperature is set, not by the cooling of the surface, but by the heat flowing upward from the even hotter core, where everything that matters happens in darkness and silence and geological time. In a realm that has never been visited, never been sampled directly, never been illuminated by anything except the faint traces of seismic waves passing through on their way from one earthquake to the next seismometer. And still, as vast as the lower mantle is, as remote and extreme and removed from everyday experience, we are not yet at the deepest part of the planet, not yet at the boundary where rock gives way to metal, where the solid mantle meets the liquid core, where the final and perhaps strangest transition awaits at the very foundation of the Earth's structure. At the very base of the mantle, in the last 200 or 300 kilometers before rock gives way to liquid metal, the structure of the Earth becomes strange in ways that seismic data can detect but cannot fully explain. This region, called the D layer, named with the kind of austere notation scientists use when they discover something before they understand it, exhibits properties that do not fit neatly into the patterns established in the mantle above. Seismic waves passing through this zone slow down in some places and speed up in others, creating a patchwork of velocity anomalies that suggest the rock here is not uniform, not simply a continuation of the lower mantle, but something different, something altered by proximity to the core, by the extreme temperatures and pressures that exist at the boundary between the solid silicate world above and the liquid iron world below. The pressure here exceeds 1 million atmospheres, forces so immense that they would compress lead into something denser than gold, that transform the behavior of electrons within atoms, that push matter into regimes where quantum mechanical effects become significant, and classical intuitions about how materials should behave begin to fail. The temperature at the base of the mantle approaches 4,000 degrees Celsius, hotter than the surface of many stars, hot enough that if this rock were somehow brought to the surface, it would glow white, would radiate heat so intensely that you could not approach within miles of it without being incinerated, and yet it remains solid, held together by pressures that overwhelm the thermal energy trying to disorder it, locked into crystalline structures that can only exist under these buried conditions. This heat is coming primarily from below, from the outer core, which is even hotter, perhaps 5,000 degrees at its upper boundary, and the temperature gradient between core and mantle is steep, creating what geophysicists call a thermal boundary layer, a zone where heat is being transferred from the liquid metal below into the solid rock above, where temperature changes rapidly over relatively short distances, where thermal instabilities can develop, where hot blobs of mantle rock may detach and begin rising toward the surface, forming the mantle plumes that eventually reach the lithosphere and produce volcanic hotspots. In some regions of the D layer, seismic waves slow down dramatically, sometimes losing 30% of their velocity over vertical distances of just a few kilometers, creating what are called ultra-low velocity zones, thin layers of material at the very base of the mantle, whose properties are so different from normal mantle rock that they must either be partially molten, their crystal structures beginning to break down under the extreme heat, or chemically distinct, perhaps enriched in iron or other heavy elements that have settled downward over geological time, accumulating at the bottom of the mantle like sediment settling to the bottom of a lake. These zones are not continuous, not a global layer wrapping around the core, but appear as isolated patches, their extent and thickness varying from place to place, their origins still debated among geophysicists who study them through the subtle distortions they impose on seismic waves that graze the core mantle boundary. The bridgemanite that dominates the lower mantle above transforms at these depths into an even denser mineral called post-perovskite, a phase that can only exist under the most extreme conditions. Discovered first in laboratory experiments and only later confirmed to exist in the Earth through careful analysis of seismic data from deep earthquakes. This transformation creates another seismic discontinuity, another abrupt change in wave velocities, Another boundary that marks a fundamental shift in the atomic arrangement of the rock, and the depth at which this transformation occurs varies depending on temperature. Shallower where the mantle is hotter, deeper where it is cooler, creating a topography to the post-perovskite transition that mirrors the thermal structure of the lowermost mantle, allowing seismologists to map temperature, variations at depths that can never be measured directly. Scattered across the base of the mantle, revealed by seismic tomography as enormous regions where shear waves travel more slowly than expected, are two continent-sized masses of anomalous material called large, low shear velocity provinces, one beneath Africa and one beneath the Pacific Ocean, each one thousands of kilometers across and hundreds of kilometers thick. Their origins mysterious, their compositions uncertain. Some geophysicists believe these provinces are the graveyards of subducted oceanic lithosphere, accumulated over billions of years, cold slabs that have descended from the surface and piled up at the base of the mantle, too dense to rise again, slowly warming but never fully equilibrating with their surroundings, preserving in their chemistry a record of ancient surface conditions, of rocks that once sat at the bottom of long-vanished oceans and have now come to rest at the bottom of the mantle. Others suggest these masses are primordial, remnants of the early Earth that have never fully mixed into the convecting mantle, isolated pockets of material with a composition closer to the original undifferentiated planet, enriched in iron and other heavy elements, denser than normal mantle rock and therefore gravitationally stable at the base, resistant to being stirred upward by convection. The boundary between the mantle and the core, called the core-mantle boundary or sometimes the Gutenberg discontinuity, is the most dramatic interface in the entire planet, a transition not just from one mineral assemblage to another, but from silicate rock to liquid metal, from a mantle made of oxygen and silicon and magnesium to a core made of iron and nickel, from a solid that flows over geological time to a liquid that flows much more freely, from a transparent medium to seismic shear waves to a medium that cannot transmit shear waves at all because liquids have no rigidity, cannot sustain shear stress, respond to any sideways force by flowing. Seismic waves reflect off this boundary, bounce back toward the surface, their reflections mapping the topography of the core's upper surface, revealing that it is not perfectly smooth, but has hills and valleys with vertical relief of several kilometers, features created by the flow of liquid iron below, by thermal plumes rising in the core and cold downwellings sinking, by the interaction between the churning metal ocean beneath and the overlying rocky mantle. The contrast in properties across this boundary is almost absolute. Above it, in the lowermost mantle, the rock is solid, rigid on short timescales, capable of supporting mountains and transmitting seismic shear waves and maintaining elastic stresses over millions of years. Below it, in the outer core, the iron is liquid, flows freely on timescales of decades to centuries, convects vigorously, generates the Earth's magnetic field through dynamo action, churns continuously in response to thermal and compositional buoyancy forces. The density jump across the boundary is substantial. Mantle rock at the base has a density of about 5.5 grams per cubic centimeter, while the liquid iron at the top of the outer core has a density of nearly 10 grams per cubic centimeter, almost twice as heavy, the heaviest material in the Earth concentrated at its center by gravitational sorting that occurred early in the planet's history when the entire Earth was hot enough for metal to separate from silicate and sink toward the middle. And yet despite this dramatic transition, despite crossing from rock into metal, from solid into liquid, we are not yet at the center, not yet at the deepest point. The outer core itself extends downward for another 2,000 kilometers, a vast ocean of molten iron that we must still traverse before reaching the final boundary, the final transition, the solid inner core that sits at the very heart of the planet like a seed suspended in fluid, isolated and unreachable, the last and most remote region in our long descent through the layers beneath the crust. Cross the core mantle boundary and you enter an ocean. Not an ocean of water, not anything that would resemble the fluid bodies we know at the surface, but an ocean nonetheless, a vast sphere of liquid metal, iron alloyed with nickel and lighter elements, flowing in currents that span thousands of kilometers, circulating in patterns driven by heat and by the slow crystallization of the inner core below, moving fast enough that the flow can be detected indirectly through its effects on the Earth's magnetic field, which shifts and wanders measurably over decades and centuries as the conducting fluid beneath reorganizes itself. As eddies form and dissipate, as convection cells strengthen in some regions and weaken in others. This is the outer core, and it extends from the base of the mantle at 2,900 kilometers depth downward to 5,150 kilometers. A liquid shell 2,250 kilometers thick, larger in radius than the planet Mars, containing more iron than exists in all of the asteroids in the solar system combined, hidden completely from view, but absolutely essential to the existence of life on the surface in ways that most people never consider. The temperature here is perhaps 5,000 degrees Celsius near the top of the outer core, rising to perhaps 6,000 degrees near the boundary, with the inner core below, temperatures comparable to the surface of the sun. And yet the iron remains liquid, because the pressure, though immense, rising from about 1.4 million atmospheres at the top to over 3 million atmospheres at the bottom, is not quite high enough to solidify it, not sufficient to overcome the thermal energy of the atoms, which vibrate and jostle with enough intensity to prevent them from locking into a crystalline lattice. The iron flows, swirls, convects with a vigor far greater than the solid mantle above, its viscosity closer to that of water than to honey, low enough that currents can develop and propagate on human timescales, that the flow patterns can change noticeably within decades, that the entire fluid shell mixes and circulates on timescales of thousands of years, rather than the millions or billions required for solid-state convection in the mantle. What drives this flow is partly heat. The outer core is hotter at the bottom than at the top, creating thermal buoyancy that causes hot iron to rise and cooler iron to sink. But also, crucially, composition. At the boundary with the solid inner core, pure iron crystallizes and joins the growing inner core, while lighter elements dissolved in the liquid, sulfur, oxygen, silicon, are excluded from the solid phase and remain in the fluid, making the liquid near the inner core boundary slightly less dense than the liquid further out, creating compositional buoyancy that drives upward flow independent of temperature. This is a self-sustaining process. As the Earth slowly cools over billions of years, the inner core gradually grows, crystallizing more iron from the liquid outer core, releasing more light elements, generating more compositional convection, maintaining the dynamo even as the planet's internal heat slowly diminishes. The magnetic field generated by this flowing metal is not a minor feature of the Earth, not a curiosity observed only by compasses and migrating birds, but a fundamental shield without which the surface would be uninhabitable. The field extends tens of thousands of kilometers into space, far beyond the atmosphere, deflecting the solar wind, the stream of charged particles flowing constantly outward from the sun, preventing it from stripping away the atmosphere, from ionizing the upper layers and gradually eroding them into space the way Mars lost its atmosphere after its internal dynamo failed and its magnetic field collapsed billions of years ago. Without the outer core's convection, without the dynamo generating the field, the Earth's surface would be bathed in radiation, the atmosphere would thin, the oceans would evaporate, and any complex life that managed to survive would be confined to deep caves or underground refuges, shielded by rock from the particle bombardment that would make the surface sterile. The mechanism by which flowing liquid iron generates a magnetic field is complex, involving the interplay between motion, electrical currents, and magnetic fields, in what physicists call a self-sustaining dynamo. The iron in the outer core is electrically conductive, and when it flows through an existing magnetic field, electric currents are induced in the fluid, according to the laws of electromagnetic induction, the same principle that governs generators and electric motors. These currents, in turn, generate their own magnetic fields, and if the flow pattern is right, if the geometry of the convection is such that the generated field reinforces the original field rather than cancelling it, the system can sustain itself, the flow maintaining the field, and the field influencing the flow in a feedback loop that has been operating for at least 3.5 billion years, possibly longer, since the earliest evidence of a magnetic field preserved in ancient rocks. The field itself is not static, not a simple bar magnet aligned with the Earth's rotation axis, but a complex, time-varying structure that wanders and fluctuates, its north and south magnetic poles drifting across the surface, sometimes moving dozens of kilometers per year, sometimes reversing entirely so that compasses point south instead of north, flipping at irregular intervals ranging from tens of thousands to millions of years. The reversals recorded in the magnetization of volcanic rocks that cooled and locked in the direction of the field at the time of their formation. The most recent reversal occurred about 780,000 years ago, and another could happen at any time. There is some evidence that the field is currently weakening, that the dipole component is decreasing, while the higher-order multipole components are becoming more prominent, patterns that sometimes precede a reversal, though the timescales are uncertain and predictions are nearly impossible because the dynamo is a chaotic system, sensitive to initial conditions, governed by equations that have no simple solutions. What strikes you as you imagine floating in this ocean of molten iron, suspended somehow in fluid, heated to solar temperatures, surrounded by metal, flowing in turbulent currents that generate invisible fields, extending into space, is how utterly disconnected this realm is from the surface, and yet how intimately connected it remains to everything that happens there. The people walking above, thousands of kilometers overhead, owe their existence to this buried dynamo, to the shield it creates, to the magnetic envelope that has protected the planet's atmosphere and water and evolving biosphere for billions of years. The outer core does not know this, does not care, operates according to physical laws that would function identically whether life existed at the surface or not, and yet without it, without this specific configuration of liquid metal convecting in just the right way to sustain a dynamo, the Earth would be as barren as Mars, as lifeless as the Moon, another rocky world orbiting the Sun with no story to tell beyond geology. And deeper still, beneath this churning ocean of iron, at a depth of 5,150 kilometers, lies one final boundary, one last transition, the place where the liquid freezes into solid metal, where the inner core begins, a sphere of crystalline iron suspended at the center of the planet, growing slowly as the Earth cools, isolated from everything, the deepest place that exists, the endpoint of our descent through the hidden architecture beneath the crust. At the center of the Earth, beneath everything, beneath the crust and the mantle and the churning ocean of liquid iron, lies a sphere of solid metal, roughly 1,200 kilometers in radius, about 3/4 the size of the Moon, suspended in the fluid outer core like a world within a world, rotating at a slightly different rate than the mantle and crust above, isolated and inaccessible, the last boundary in the planet's layered structure. This is the inner core, and it is solid, not because it is cooler than the liquid surrounding it. In fact, it may be slightly hotter, perhaps 6,000 degrees Celsius, at the very center, but because the pressure here, exceeding 3.5 million atmospheres, is so immense that it forces the iron atoms into a crystalline lattice, locks them into an ordered arrangement. Despite the intense thermal vibration, compresses them into a state that can only be described as solid, even though the temperature is far above the melting point at any lower pressure. The iron here is not just compressed, but fundamentally altered, its electrons behaving in ways that require quantum mechanics to fully describe, its atomic structure adapted to conditions that exist nowhere else in the solar system, except perhaps in the cores of other rocky planets, if they have managed to differentiate and cool in similar ways. The inner core is growing very slowly, as the Earth continues to lose heat to space, continues to cool from the outside inward. Each year, a thin layer of iron crystallizes onto the surface of the inner core, freezing out of the liquid outer core above, adding perhaps a millimeter to the radius over the course of a millennium, a rate so slow that the inner core has grown by only a few hundred kilometers since it first began to form, perhaps 1 billion years ago, perhaps less. the exact age still uncertain because the growth rate depends on the cooling rate and the composition of the core and other factors that are difficult to constrain from surface observations alone. When the inner core first nucleated, when the center of the Earth first became cool enough for solid iron to be stable, it would have been tiny, perhaps just a small seed crystal, a nucleus around which more iron could accumulate, and it has been growing steadily ever since, consuming the liquid outer core bit by bit, shrinking the fluid shell while expanding the solid sphere, a process that will continue for billions of years into the future until eventually, in the distant, unimaginable future. When the Earth has cooled sufficiently, the entire core might solidify, the liquid shell disappearing entirely, the dynamo shutting down, the magnetic field collapsing, the planet becoming geologically dead. The structure of the inner core is not entirely understood. Seismic waves traveling through it behave strangely, traveling faster when they move parallel to the Earth's rotation axis than when they move along the equator, an anisotropy that suggests the iron crystals are aligned, oriented preferentially in one direction, perhaps by the flow of the liquid outer core above, perhaps by the slow convection that may occur even within the solid inner core itself at these extreme temperatures and pressures. Some seismologists have detected evidence of layering within the inner core, concentric shells with different seismic properties, possibly representing different episodes of growth or different crystalline phases of iron that become stable at different depths. There are even hints of an innermost inner core, a central region a few hundred kilometers in radius where the seismic anisotropy is different, where the crystal alignment shifts, suggesting some kind of boundary or transition that occurs deep within the solid metal sphere, though the evidence remains ambiguous and the interpretation controversial. The boundary between the liquid outer core and the solid inner core is sharp, abrupt, a freezing front where iron changes phase from liquid to solid over a distance of perhaps just a few kilometers, releasing latent heat as it solidifies, heat that is absorbed by the surrounding liquid and contributes to the buoyancy driving convection in the outer core. This boundary is not static, but moves upward and downward slightly in response to temperature fluctuations in the core, to variations in the rate of heat loss to the mantle above, to the complex dynamics of the dynamo, its surface possibly rough, possibly studded with growing crystals or melting regions where local temperatures fluctuate above or below the freezing point. Seismic reflections from this boundary can be detected and analyzed, their travel times and amplitudes providing information about the sharpness of the transition, the density contrast between liquid and solid, the detailed structure of the freezing interface. Standing here in imagination, at the center of the Earth, you would be standing at a depth of 6,371 kilometers below the surface, the exact radius of the planet, the maximum distance it is possible to be from the open air and sunlight and the familiar world of the crust. The pressure surrounding you would be approximately 3.6 million atmospheres, a force so great that it defies easy analogy, that compresses iron to a density of about 13 grams per cubic centimeter, nearly twice its density at the surface, packing the atoms into a space barely half the volume they would occupy under normal conditions. The temperature would be roughly equal to the surface temperature of the sun, hot enough to emit light in the visible spectrum, if there were any way for that light to escape, if it were not absorbed and scattered by the thousands of kilometers of overlying material, converted to heat long before it could reach the surface. And yet, for all its extremity, for all the dramatic numbers describing pressure and temperature and depth, the inner core is also, in a sense, the simplest part of the Earth, the most uniform, the least complex. It is made of iron and nickel in approximately the same proportions as meteorites, the same composition as the undifferentiated material from which the solar system formed, purified slightly by the exclusion of lighter elements, but still fundamentally primordial, still carrying in its chemistry the signature of the planet's origin. It does not convect vigorously like the outer core or the mantle. It does not participate directly in plate tectonics or volcanism or any of the surface processes that make the Earth geologically active. It simply exists, grows slowly, radiates heat outward, rotates at its own pace, isolated and remote, a sphere of solid metal that has been sitting at the center of the planet for a significant fraction of Earth's history, and will continue sitting there, gradually expanding, until the planet cools beyond the point where the outer core can remain liquid. What you feel, if you allow yourself to truly contemplate this depth, this distance from everything familiar, is not just the physical extremity of the conditions, but the temporal enormity of what you are imagining. The iron at the center of the inner core has been solid for hundreds of millions of years, possibly a billion, locked in crystalline form under pressures that will never diminish, at temperatures that will cool only on timescales measured in billions of years. The atoms making up this metal were forged in the heart of a dying star, expelled into space, incorporated into the solar nebula, accreted into the proto-Earth, separated from lighter elements as the young planet melted and differentiated, and have been sitting at the center ever since, participating in the slow cooling of the planet, in the gradual loss of primordial heat to space, in the long arc of geological history that will eventually see the Earth become cold and dead and silent, though that ending lies so far in the future that the sun itself will have exhausted its hydrogen and begun to swell into a red giant before the Earth's core fully solidifies. And now, having reached the deepest point, the center, the place from which all distances are measured upward, we must pause and consider what it means to have descended through this structure, to have traversed in imagination the full depth of the planet beneath the crust, from the familiar surface down through layers that become progressively stranger, hotter, denser, more remote from human experience, until arriving here, at a place that no human could ever reach, that no probe could ever sample, that exists entirely beyond the possibility of direct observation, known only through the echoes of earthquakes, the pull of gravity, the wandering of the magnetic field, and the patient application of physics to the problem of what must lie below. The structures we have descended through do not exist in time the way human things exist in time. A building stands for decades, perhaps a century or two, before it crumbles or is demolished. A mountain, carved by rivers and glaciers, endures for tens of millions of years before erosion wears it down to hills and eventually to plains. But the mantle, the core, the fundamental architecture of the planet's interior, these have been in place for more than 4 billion years, since shortly after the Earth formed from the swirling disk of dust and gas surrounding the young sun, since the planet was still molten and metal was sinking toward the center, while lighter silicates rose toward the surface, separating under gravity into the layered structure that has persisted, fundamentally unchanged in its broad configuration, through nearly the entire history of the solar system. The iron core solidified from a molten state, the mantle differentiated into upper and lower regions. The crust formed as a thin solidified skin, and once these layers were established, they became permanent features, stable arrangements that have endured through ice ages and mass extinctions and the rise and fall of entire mountain ranges, through continental collisions and the opening and closing of ocean basins, through every event in Earth's history that we would consider dramatic or catastrophic, all of it occurring in the outermost skin, while the deep interior remained essentially constant, changing only slowly, cooling only incrementally, its basic structure locked in place by the physics of differentiation and the immense timescales required to remix or reorganize materials at these depths. The inner core, that solid sphere of iron at the center, is perhaps the youngest of the major layers, having formed sometime in the last billion years when the Earth had cooled enough for the pressure at the center to stabilize solid iron. But even a billion years is an almost incomprehensible span, a duration long enough for complex life to evolve from single cells to the diversity of forms that inhabit the modern Earth, long enough for entire supercontinents to assemble and break apart, multiple times, long enough for the Moon to recede measurably from Earth through tidal friction. And yet from the inner core's perspective, this entire period has been one continuous process of gradual growth, millimeter by millimeter, century by century, the solid sphere expanding as the planet slowly cools and more iron freezes onto its surface. The outer core has been liquid for far longer, perhaps since the core first separated from the mantle 4.5 billion years ago, its convection patterns shifting and reorganizing on timescales of thousands to millions of years, but the liquid state itself never changing, never solidifying except at the boundary with the growing inner core, never ceasing its flow or its dynamo action for more than brief intervals, if at all. The mantle has been solid throughout Earth's history, or at least solid in the sense of being able to transmit seismic shear waves, which is the operational definition geologists use for solidity when dealing with materials that flow over geological time. It has been convecting since the planet cooled enough to develop a rigid lithosphere, circulating heat from the deep interior outward to the surface, stirring itself slowly, homogenizing its composition over billions of years, while still preserving some chemical heterogeneities, some regions that have remained isolated from the main circulation, some pockets of primitive material that have never fully mixed with the rest. The convection rate has changed over time as the planet cooled. It was probably more vigorous early in Earth's history when the interior was hotter and temperature gradients were steeper, and it will slow further in the future as the temperature continues to drop. But the basic pattern has remained: hot material rising and cool material sinking, the cycle repeating endlessly, transporting heat and reshaping the surface through the side effects of its motion. The crust is the youngest layer, constantly being created and destroyed, recycled through plate tectonics on timescales of hundreds of millions of years for oceanic crust, and much longer for continental crust, some portions of which date back more than 4 billion years, preserving in their mineral structures a record of the early Earth, of conditions that existed when the planet was still being bombarded by asteroids, when the atmosphere was devoid of oxygen, when the surface was so hot that the oceans may have been partially or completely evaporated during brief violent intervals. But even these ancient crustal rocks are young compared to the core, young compared to the mantle, young in the sense that they formed from materials that were once part of the mantle, and will eventually return to the mantle through subduction, completing a cycle that the deep interior does not participate in, remaining isolated below, stirring slowly but never returning to the surface, never rejoining the rapid exchange of materials that characterizes the shallow Earth. The timescales on which these deep structures change are so long that they become almost meaningless when compared to human experience. The mantle convection cell that is currently rising beneath the mid-Atlantic ridge and sinking beneath the Pacific subduction zones will take 100 million years to complete one full circulation, to return material from depth to the surface and back to depth again. The inner core grows by perhaps 1 millimeter per millennium, meaning that the outermost layer of the inner core, the iron that is currently freezing onto its surface, will be buried beneath hundreds of meters of subsequently frozen material before human civilization, if it survives that long, reaches even a fraction of the age that some geological formations have already achieved. The lower mantle, that vast region between 660 and 2,900 kilometers depth, may mix on timescales of 1 billion years or more, meaning that a parcel of rock currently sitting at the base of the lower mantle might not reach the upper mantle for longer than the entire duration of complex life on Earth. What this means is that the planet beneath our feet is not responding to anything we do, is not reacting to human activity or to any surface process on timescales we can perceive. When an earthquake occurs, when a volcano erupts, when a mountain range rises or a coastline erodes, these are not spontaneous events, but the surface manifestation of processes that began thousands or millions of years earlier. Processes involving the slow movement of tectonic plates, the gradual accumulation of stress in the crust, the ascent of magma that was generated deep in the mantle long before it reached the surface. The deep Earth operates on its own timescale, indifferent to the rapid fluctuations of climate and biology and human history that unfold in the thin layer at the top, connected to the surface only through the slow mechanical coupling of mantle convection driving plate motion, through the heat that escapes upward and powers volcanism, through the magnetic field generated in the core that shields the atmosphere from erosion. And yet, despite this profound disconnect in timescales, despite the fact that the deep Earth changes so slowly that it might as well be eternal from a human perspective, it is changing, is cooling, is evolving toward a state of lower energy, of equilibrium with the cold vacuum of space. The Earth is not a perpetual motion machine, not a system that maintains itself indefinitely without loss, but a slowly cooling body, radiating heat into space at a rate of about 44 trillion watts. A power output that sounds enormous until you realize it represents the gradual dissipation of heat that has been stored in the planet since its formation. Heat that is finite, that cannot be replenished, that will eventually run out. The core is cooling by perhaps 50 to 100 degrees Celsius every billion years, a rate so slow that it will take tens of billions of years for the core to freeze completely, longer than the remaining lifetime of the Sun, longer than the Earth will exist as a habitable planet. But the direction is clear, the trend is irreversible, and the endpoint is a cold, geologically dead world, its core solid, its mantle static, its magnetic field gone, its surface frozen and unchanging, a fate that has already overtaken Mars and the Moon, and will eventually overtake Earth as well, given enough time. But that future is so distant, so removed from any conceivable human concern, that it might as well be infinite, and what remains relevant is the present, the fact that the Earth as it exists now is geologically active, dynamically alive, reshaping itself continuously through processes powered by its internal heat, by the slow cooling of its deep interior, by the convection of the mantle and the flow of the outer core and the growth of the inner core, all of it happening beneath our feet. Invisible, but absolutely essential to the world we inhabit. To understand what exists beneath the crust is not merely to catalogue layers, not simply to list their depths and temperatures and compositions, but to recognize that these layers form a system, an integrated whole, where each part influences the others, where heat flows from core to surface, where motion in one region drives motion elsewhere, where the planet functions as a coupled thermal and mechanical engine that has been running for billions of years and will continue running until its fuel, the stored heat from formation, and the ongoing decay of radioactive isotopes, is finally exhausted. The Earth is not a static stack of different materials, but a dynamic body in which the solid inner core grows and releases heat. The liquid outer core convects and generates a magnetic field. The mantle circulates and drives plate tectonics, and the crust fractures and reforms and participates in the surface expression of these deep processes. All of it connected, all of it part of a single ongoing process of planetary heat loss and internal reorganization. The heat generated in the core, both from the slow crystallization of the inner core releasing latent heat, and from radioactive decay of the small amounts of uranium and thorium that may be dissolved in the liquid iron, flows upward into the base of the mantle, where it is absorbed by the lowermost mantle rock, making it less dense, causing it to rise, initiating convection that carries the heat upward through the mantle over millions of years until it reaches the base of the lithosphere. There, because the lithosphere is too cold and rigid to convect, the heat must be conducted upward through solid rock, moving slowly, leaking out through volcanism at plate boundaries, through the creation of new oceanic crust at mid-ocean ridges, through the general geothermal gradient that makes mines and deep boreholes measurably warmer the deeper you go. This heat flow is continuous, relentless, averaging about 44 trillion watts globally, enough power to run human civilization many times over if it could be captured, though most of it escapes into space unnoticed, radiated away from the surface as infrared light, carrying away the planet's internal energy bit by bit, year by year, gradually cooling the interior. The mantle's convection is not isolated from the core's behavior. When the outer core convects more vigorously, when the dynamo strengthens or reorganizes, the heat flux from core to mantle changes, and this changes the temperature at the base of the mantle, which changes the buoyancy forces driving mantle convection, which changes the rate at which heat is transported upward, which eventually affects the rate of seafloor spreading and the vigor of plate tectonics at the surface. The coupling is indirect, filtered through thousands of kilometers of intervening rock and buffered by the immense thermal inertia of the mantle, but it is real, measurable in principle, if not yet in practice. A connection between the deepest interior and the surface that operates on timescales of millions to hundreds of millions of years, invisible to human observation, but fundamental to the planet's long-term evolution. Similarly, the mantle's convection influences the core. Cold slabs of subducted lithosphere descending through the mantle, eventually reach the core mantle boundary, where they pile up, creating regions of anomalously cold mantle rock sitting directly above the liquid iron, increasing the rate of heat extraction from the core in those locations, potentially influencing the pattern of convection in the outer core, possibly even affecting the structure and stability of the magnetic field generated by the dynamo. The large low-shear velocity provinces at the base of the mantle, those continent-sized masses of anomalous material beneath Africa and the Pacific, may be influencing the flow patterns in the outer core, creating preferred locations for upwelling or downwelling in the liquid metal, shaping the magnetic field in ways that leave signatures observable at the surface, though the exact mechanisms remain uncertain, still being investigated through computer simulations and seismic analysis. The whole system, from surface to center, is coupled through heat flow and through the mechanical interaction of flowing materials at different depths. Plate tectonics at the surface is the visible manifestation of mantle convection, which is driven by core cooling, which is influenced by the rate at which the mantle removes heat from the core mantle boundary, which depends on the vigor of mantle convection, which depends on the temperature of the core. A feedback loop that regulates itself over geological time, maintaining the Earth in a state of dynamic equilibrium where heat generation and heat loss are roughly balanced, where the interior cools slowly but not catastrophically, where geological activity persists but does not accelerate beyond sustainable levels. What emerges from this synthesis is an image of the Earth as a layered sphere, yes, but more fundamentally as a heat engine, a machine for converting stored thermal energy into mechanical work, into the motion of tectonic plates and the flow of mantle rock and the circulation of liquid iron, into the fracturing of the crust and the eruption of volcanoes and the slow drift of continents across the surface. The energy source is finite, the heat stored during the planet's formation, plus the heat being generated by radioactive decay, which diminishes over time as the long-lived isotopes slowly transform into stable elements. And so, the engine is gradually winding down, losing power, cooling toward an eventual state of equilibrium with space. But the timescale is so long, the thermal reserve so vast, that the engine will run for billions of years more before it finally stops. And the scale of this engine, the sheer volume of material involved, the depth through which heat must travel to escape, these dimensions are so enormous that they challenge comprehension even when stated numerically. The mantle alone contains more than 80% of the Earth's volume, more than 1 trillion cubic kilometers of rock, all of it moving, all of it participating in the slow convection that drives surface geology. The outer core contains another 16% of the planet's volume, 200 million cubic kilometers of liquid iron, all of it flowing, all of it contributing to the dynamo. The crust, which seems so substantial from our perspective standing on it, amounts to less than 1% of the Earth's volume, a rounding error in the planet's overall structure. And yet it is the only part we can directly observe, the only part we can sample and study in detail, the only part that is accessible to our instruments and our understanding. Beneath that accessible layer lies everything else, the vast bulk of the planet, known only indirectly, mapped only through inference, understood only by applying physical laws to the echoes of earthquakes and the pull of gravity and the wandering of magnetic field lines. We have never seen the mantle directly, never sampled the outer core, never touched the inner core, and we never will, because the depths are too great, the temperatures too high, the pressures too extreme for any conceivable technology to penetrate. And yet we know these layers exist, know their approximate compositions and temperatures and thicknesses, know how they behave and how they interact, because the laws of physics are universal, because seismic waves propagate according to predictable rules, because density and pressure and temperature are related through equations of state that can be measured in laboratories and extrapolated to conditions that exist nowhere on Earth's surface, but everywhere in its interior. What this means is that our understanding of the deep Earth is fundamentally different from our understanding of the surface. At the surface, we can observe directly, can touch and measure and experiment with the materials in front of us. Below the surface, we must infer, must interpret, must construct models that are consistent with the limited data available, and hope that those models capture the essential truth of what lies below, knowing that the models will always be incomplete, always be approximations, always be subject to revision as new data arrives or as computational techniques improve, or as someone thinks of a new way to test the assumptions that underlie our current understanding. And yet, despite these limitations, despite the fact that we are essentially blind to most of the planet's interior, the picture that has emerged is remarkably coherent, remarkably consistent across different types of measurements, remarkably successful at explaining not just the structure of the Earth, but its history, its evolution, its continuing transformation. And so we return to the surface, to the cool night air and the quiet darkness, to the ground beneath our feet that feels no different than it did before, still solid, still reassuring, still holding everything above it with the same patient strength it has maintained for billions of years. The journey downward through those layers, through crust and mantle and core, through depths measured in thousands of kilometers and temperatures measured in thousands of degrees, was always imaginary, always a construction of thought attempting to follow where the body cannot go. And yet something has changed in the understanding, in the way the ground feels when you know what lies below it, when you have some sense, however incomplete, of the vast architecture that extends downward into darkness, supporting the thin surface world where all familiar things exist. The Earth does not ask to be understood. It continues its slow work, regardless of whether anyone is paying attention, regardless of whether the mantle's convection is being measured, or the core's magnetic field is being mapped, or the inner core's growth rate is being calculated. The planet existed for more than 4 billion years before anything capable of wondering about its interior evolved on its surface, and it will continue existing long after that brief episode of curiosity has ended, cooling slowly, circulating its heat, reshaping its crust, generating its magnetic field, operating according to physical laws that require no observer, no interpretation, no appreciation. The iron at the center will keep crystallizing, millimeter by millimeter, century by century. The mantle will keep convecting, rising in some places and sinking in others, transporting heat upward at a pace too slow to perceive, but fast enough to move continents. The outer core will keep flowing, generating the magnetic shield that makes the surface habitable, protecting the atmosphere from the solar wind with a field that wanders and fluctuates but never fails, not yet, not for billions of years of continuous operation. What we have traced, in descending through these layers, is not a path that anyone will ever physically travel, but a structure that has been revealed through patience, through the accumulation of observations over centuries, through the careful listening to earthquakes and the measuring of gravity and the analysis of how the magnetic field shifts over time, all of it pointing toward the same conclusion, that the planet is far deeper and stranger than the surface suggests, that most of its volume exists in states and at scales completely removed from everyday experience, and that this hidden bulk is not inert but active, not static but moving, participating in processes so slow they become invisible but so powerful they reshape the entire surface over geological time. The ground is thin, what lies beneath is vast. And the thinness of the ground, the fact that we exist in the shallowest possible fraction of the planet's total depth, makes the surface both fragile and precious, a narrow zone where temperatures are mild enough for liquid water, where pressures are low enough for complex chemistry, where conditions permit the existence of life in forms that could not survive anywhere deeper. Perhaps the most honest response to this scale is not wonder, though wonder is natural, but a kind of quiet recognition that the world extends far beyond what we can see or touch, that the familiar is underlain by the unfamiliar, that the thin layer of accessibility rests on thousands of kilometers of inaccessible depth, and that this arrangement is not a problem to be solved, but simply the way things are, the structure of the planet we happen to inhabit, the context within which everything we know takes place. The crust will continue being thin, the mantle will continue being thick, the core will continue being hot and mostly liquid and unreachable, and we will continue standing on the surface, looking down when we remember to, imagining what exists below, constructing models and testing hypotheses, and refining our understanding incrementally, knowing that the full truth will always remain slightly beyond our grasp, always be mediated through instruments and mathematics and inference, never directly seen, never fully confirmed. The night is still quiet. The wind still moves through distant trees. The ground still feels solid beneath you. And perhaps now, having descended in thought through all those layers, having followed the temperature upward from 6,000 degrees at the center to the cool surface air, having witnessed the scale of what exists below, you can rest a little more easily, knowing that the planet is deeper than worry, older than anxiety, more patient than any human concern, and that it will continue its work long after you have stopped thinking about it, long after. You have fallen asleep, long after the questions have faded, and only the quiet remains. If this journey brought you a sense of calm, you can subscribe to Quiet Science and continue exploring these silent depths with us.